Okay, so this is the analytic Jacobian for the case of a planar 2R manipulator when the task variable are the two coordinates of the position of the origin of the frame attached to the end effector and the absolute orientation in the plane. So this is a 3×2 matrix. Let's do another example. This is the polar robot that we have considered already for the direct and inverse kinematics. This is, here we consider the three coordinate of the position of the tip. We have n equals 3 joints, so this is the direct kinematics. And taking the time derivative, but now we learn that we just need to take the partial derivative of the expression in the direct kinematics and then with respect to q and then multiply by q dot. This will be the Jacobian for this particular task. Remember that you can consider the same robot and other kinematic functions, so you may have at the analytic level multiple Jacobian depending on what you're interested into. Okay, in this case, since this is the r vector was p, so r dot is p dot, which is also the linear velocity of the end effector. Okay, and so on and so on. Now let's move to the other way of generating a Jacobian, so the Jacobian, geometric Jacobian. This is always a 6×n matrix. Relates the joint velocity q1 dot to kn dot to the three component of the linear velocity of the end effector and of the angular velocity of the frame attached to the end effector. So here you see that we can partition always this 6×n matrix in two blocks by rows. The top three blocks, which relates to the linear part, and the bottom three, which relates to the angular part. And then, as any product of a matrix times a vector, you can always write this product as the combination of the columns of the matrix, each weighted by the associated component of the vector which follows. Okay? So if we split this in two, the linear velocity of the end effector is the first top part of the column, of the first column times q1 dot, then the second column, and so on times each its associated joint velocity. And similarly for the bottom part, first columns times the velocity of first joint, second columns second velocity, and so on. And this gives omega, which means that now the order is irrelevant, that we can work with this principle of superposition of effects. So we just move one joint and look at its contribution both to the angular and to the linear velocity. And if we are able to write this contribution in a generic form, and we will split two cases, if the joint is prismatic or if the joint is revolute, then we just repeat this for all possible joints, we sum, and we have the expression both of the linear and angular velocity, but in between, by factoring out the joint velocity, also of the geometric Jacobian. Okay? It's not much difficult. Okay? And remember, all this can be done because we are working with vector, or we're working in linear spaces. So, now consider a generic joint in the structure, and the simplest case is the prismatic joint. So here we have the base, we have a joint link up to the generic joint I, and we assume that this joint is prismatic. So let's define something. So the axis of the joint, according to the Dynavit-Artenberg convention, is zi minus 1 of the frame I minus 1, remember this, and the variable of this joint is a di. Okay. Now you give a velocity to this joint, which means that you give a di dot, and so you will move along this axis. what is before is not moving, and all what is behind is translating without other motion, because we are freezing all the joints except this one. We are looking at the contribution of this single joint. Okay, so I think that is rather obvious that if we move along this joint linearly, everything will translate in the same way up to the end effector. Okay? Or stated differently, there will be no angular contribution due to the motion of a prismatic joint, which makes sense. Okay? So, how do we write this? We said that the linear part of this joint, if joint I is prismatic, will be JLI QI dot, and will be equal to the velocity that I'm giving with this joint. And what is this velocity? Is a vector aligned with Zi minus 1 with intensity di dot. So this expression for the prismatic joint is given by that. And now you can associate things. You say that Qi dot is di dot. This is the scalar. So this piece of column of the Jacobian is nothing else than the unit vector Zi minus 1 of joint I. What about angular velocity? Well, this does not contribute to angular velocity because it does not rotate anything. So this will be 0. So there's no vector there, which means that independently of what is the value of this, which means that this part, the lower part of the ith column of the geometric Jacobian when the joint is prismatic will be 0. Okay? This is simple. Same thing we do for a revolute joint, but this is more technical. So again, everything what is before is frozen. Everything what is behind is frozen. So this is not moving. I'm giving a rotation around this joint axis, and all what follows is a single body that rotates around the joint axis I. Again, what is the axis of this joint is Zi minus 1. What is the variable is theta. So when I give a velocity, I will have an intensity theta I dot around this axis. Okay? So what will happen at the end? Well, this is just like moving. So this is a single body. I'm imposing an angular velocity, so the angular velocity which will be exactly what I'm imposing. So a rotation of intensity theta I dot and direction Zi minus 1. But when I'm rotating and I'm considering a point which is out of the rotation axis, this point will have also a linear velocity. As simple as that. So there will be some distance and a vector product of the distance times the intensity of the angular velocity. So these two contributions will be written in this way. And pay attention now. So the angular part is easy. Why? Because it's exactly the angular velocity that I'm imposing with this joint. So directed along Zi minus 1 and with intensity theta I dot. So if I compare this expression to the generic contribution of the lower part of the ith column of the Jacobian when the ith joint is revolute, Qi dot will be theta I dot. So this JAI vector will be Zi minus 1. It's just the reverse of the previous case. Now this requires some additional comment. Here I'm making the product of this angular velocity, Zi minus 1 theta I dot. The scalar can be anywhere. Then vector the distance between this axis and that point. But here I'm not taking the distance actually. I'm taking a different vector which goes from the origin of frame I minus 1, which I'm sure it will be along this joint axis, to the end effector position. Here it may seem orthogonal, but it may not be orthogonal at all. So I'm taking just, for instance, if the origins was here, I'm taking the vector from here to there. So not the vector of minimum distance. Why I'm doing this? Actually, I should take, as we said before, the vector that goes, from there, orthogonal, maybe from this point in that expression. Okay? And in fact, this point, it's really hard to compute this point. But in fact, the result will be the same. Why is that? So why can I replace the vector going from here to there with this vector going from the origins of I minus 1 to E? What is the difference between these two vectors? Between this vector going from here to there and from here to there. The difference is a vector going from this minimum distance point to the origin of I minus 1. Now this vector is aligned with like Zi minus 1. So in this vector product, it just disappears. So when you have a vector product, the result will be always the same if you change the point. Any point along this joint axis will provide you the same result. Okay? So why am I choosing this pi minus 1e? Because this vector can be computed as a side results of the direct kinematics, because it goes from one origin to another origin. So it's included in the Denavit-Artenberg transformation matrices. Okay? So pay attention to this. So this is the efficient way. Now, let's collect things together. Factoring out the velocity in the two cases. So the columns of the geometric Jacobian, if the ith column is prismatic, will be this. If the ith column is revolute, will be given by this expression. Now, on top, you see that I'm writing that these columns are a function of Q. But where is Q here? Where is Q here? I don't see any Q. Why I'm saying that these are a function of Q? Well, they are hidden inside this expression. This is the orientation, the unit vector in the orientation of joint I. Well, if I'm changing my previous joint, this will change direction, so it's a function of Q. And similarly, this distance between two origins, between this origin and this, will be a function of the configuration. So the Q is buried here, and in order to show them, you have to compute them explicitly. So remember that everything is expressed in the base frame. So here I'm not writing anything, but it's like writing here a 0 here, a 0 here, and a 0 here. All vectors are expressed in the base frame. So how do I compute them? For instance, the unit vector Zi minus 1 is simply computed by the Zi minus 1 vector expressed in frame I minus 1, so 0, 0, 1. And then I have to change its representation. How do I do it? By rotation matrix. So I express this in frame I minus 2, then in I minus 3, back to frame 0. So I have this Zi minus 1 superscript 0, which I don't write because now the convention is clear. Okay, so and I see here the dependence on Q's in this term, and then in this term, and in this term. For the other one, now these are applied vectors. They go from one point, the origins of frame I minus 1, to the origins of the last frame, which I called E. Okay? So if I transform them, I should use homogeneous coordinate and 4x4 homogeneous matrices. Okay? So I'm writing this as the difference between two vectors from the base to the tip, and this is the full direct kinematic of the robot, minus from the base to the origins of frame I minus 1, which is a partial direct kinematic up to the origins of frame I minus 1. Okay? And how do I compute this? By multiplying 4x4 homogeneous Denavit-Artenberg matrices and then extracting the last column, this, removing the 1 of the 4th row and then making the difference. So I have an expression as a function of q, which I replace to this vector here. So here, you don't have to differentiate anything. You just use information that you already have in the direct kinematics, but reorganizing things properly. You extract this, you evaluate it for the current configuration, and you have the Jacobian. Okay? So we skipped it. Let's do again the same example. So now I'm assigned Denavit-Artenberg frame because I'm using this machinery in the computation. Here, it's not strictly needed. This case can be handled without. But just to point out that if you have a very complex robot, you may still use what we learned on direct kinematics. So you build the Denavit-Artenberg table, you compute the DH transformation matrices, so 4 by 4 matrices, and these are and now you're interested in the Jacobian geometric that gives you the 3 component of the linear velocity of the origins of frame 2, which is the end effector, and the 3 component of the angular velocity of this frame. Of course, this is a planar case, so I already know that the angular velocity will be only directed along the normal to the plane of motion, so it will have only a z component. Okay, but still I can compute everything. So my Jacobian is a 6 by 2 matrix, because always 3 and 3, and this is the number of joints. And since both joints are revolute, they take the general expression of revolute joints. So zeta 0 on the angular part and zeta 1 for joint 1 and 2. And here the vector product, zeta 0 times from origin to end effector, or from origins of frame 1 to end effector. So you see that P0A, I should do the product of this and then take the last column. While P1E is a different, okay, sorry. I've already done the product here. So here I read P02 or 0E, and then this is P01, so P1E is the difference between this and this. Okay, and then it's inserted there. And this is what okay. The other thing that I need is Z0 and Z1. These are very simple because these are always constant and coming out. So it's a very simple expression. So this is what I said, and the difference gives the other terms that I need. So if I do the product, vector product, symbolically, if I wish, with a symbolic toolbox of Matlab or by hand, and this is the Jacobian that I get. Okay? And not surprisingly, these 3 rows are 0. Why? Because no matter what will be the velocity of joint 1 and joint 2, so this will be multiplied by q dot, the third component gives the vz, so the linear velocity out of the plane, and the robot cannot have this velocity. Okay? So this is 0, not unexpected. Similarly, I cannot rotate out of the plane, so omega x and omega y should always be 0. So in fact, this is 0 no matter what is q1 dot and q2 dot. What is left is just vx and vy, exactly like in the analytic case, and exactly like in the analytic case, omega z is the phi dot. So this is 1 and 1. It's like having the partial derivative of q1 plus q2. In this planar case, once we remove the extra unnecessary rows, we found exactly the same situation. In fact, you can really eliminate this. Okay? Now, pay attention. This matrix, independent of the fact that some rows are 0, it's a 6 by 2 matrix, so it cannot have more than the rank of its columns. So it cannot have more than a 2 by 2 minor, which is with non-zero determinant. Which also means that out of these 6 velocities, linear components or angular components, I can command with my 2 joints at most 2 of them. The other one are consequence of this choice. So the fact that I'm using a Jacobian which apparently maps my 2 joint velocity in 6 quantities should not be misleading in the sense that I cannot control all 6 quantities. Of course, I can control at most 2 of them at the same time. Okay? Okay, I will skip this, but just to remember that this Jacobian, because we are computing everything in the base frame, so it gives the linear velocity and the angular velocity expressed in the base frame. Of course, you can re-express this in any other frame, and you can use rotation matrix, and this may simplify the structure of the Jacobian. But this is too much time to describe in detail, so we will skip this and also the example that I have. So, summary of what we have done so far at the level of differential relationship. So we have now found out that the derivative of the position, time derivative, is the velocity. And in fact, the upper part also of the Jacobian are the same if we are considering as task variable the position of the end effector. Then we have found a relationship between a generic derivative of a minimum representation of orientation, so triangle organized in an array phi, so between phi dot and omega. And in general, there is a transformation, which is a function of at most the first 2 variables if we are using moving axis. And this is the T matrix that we have computed for one case. Okay? So there's a T times phi dot gives omega. So if we are taking as task vector exactly P and phi, and this is the only case in where we can compare the analytic and the geometric Jacobian. Why? Because the top part of this, if I differentiate, is the linear velocity, and the bottom part of this phi dot is connected to omega by that relation. Okay? So if I generate the geometric Jacobian and the analytic Jacobian, the relationship between the two are as stated in the on the slide. So there's an identity here because the linear part is exactly the same, while this matrix appears in the angular relation between the 2 matrices. Okay? Which means that if I look for the singularity of one of the 2 Jacobian, in particular of the analytic Jacobian, I will include not only the singularity which are strictly related to the kinematic structure of the arm, but also the singularity of this matrix, which are only related to the way in which I want to represent the orientation of the end effector. If I'm choosing another representation, I may not have those singularity. I will have always singularity, but this may occur, for instance, out of the joint range of my manipulator. So choosing the right representation may also be a matter of convenience. And then we have also computed this relation between the time derivative of r and omega. So what can we say about higher order derivative? I will present this for the analytic case, but something similar can be said about the geometric Jacobian. The analytic case is more clearer in this sense. So we start from the velocity relationship. So we have a task vector r, and we have seen now over and over that this can be chosen in different way. We know that r dot is an analytic Jacobian of the direct kinematics times the joint velocity. What about r double dot? Well, simple. Just take the derivative once more, but here now you have 2 terms, so you differentiate this with respect to time and you keep this untouched, and this is the first contribution. And then you differentiate this with respect to time, pay attention, and leave this untouched, and you have this J dot Q dot. What does it mean to differentiate this matrix with respect to time? You don't see time there. You see only Q's. So you have to, each element should be differentiated with respect to all the variables that appears, Q1 to Qn, whatever, and each of these variables then with respect to time, so you have Q1 dot, Q2 dot, and so on. So inside this matrix, pay attention, this is a notation matter. Although I'm writing only Q because I had Q here and I have some object that I take the derivative. In fact, inside this object, there are also velocities. Okay? So you could rewrite this saying that this is a new matrix that you label N2 because it's in the second derivative. And this new matrix is a function of Q and Q dot. Why I'm saying this? Because, in fact, you will recognize that inside this product, you have a linear dependence on Q dot here, a linear dependence on Q dot here. So these terms are quadratic in Q dot. And they play the role like Coriolis or centrifugal acceleration, which are quadratic in velocity. Okay? And the product of velocity of the whole term. While this terms is, again, same matrix times the acceleration. So don't forget this part. Okay. Now, there's another important aspect. In order to compute the velocity of the task, so of the end effector, let's say, you need to know which velocity you want to command at the joint, and you have to know the configuration of the arm. So I'm here, I'm applying some velocity, I have some velocity there. If you move one step up this computation and you want to compute the acceleration of the end effector, what do you need to know? You need to know the configuration of the robot. So I'm here. The acceleration that you want to command to the joint, here, but also the velocity of the joint, because they appear here and inside this matrix. Which means that if you apply the same acceleration and the robot is at rest, so Q dot is 0, you will obtain some Cartesian acceleration. If you apply joint acceleration when the robot has already a velocity, you will have also this term, so you will obtain another acceleration. So pay attention. At the first level, you need to know the state of the robot, and this state is just the configuration, and then you apply velocity. At the second level, the state of the robot is position and velocity, and then you choose acceleration of the joint, and you compute the acceleration. And so on and so on. In fact, if you repeat this for the third order, okay, now you have multiple terms. Pay attention how the differentiation occurs. So you take this term, you take the derivative with respect to time for this, and you leave this untouched, so you have this contribution. Then you take the derivative of this, and you have Q double dot, so you have J dot, Q double dot, and this is the first of these two contributions. The second comes from here, because here again you have a product. You take the derivative of this, and you leave this untouched, and you have J dot, Q double dot, and this is the second contribution here. And finally, you leave this untouched, and you have the second derivative of this, and you have this one. And again, inside this matrix, since you have two derivatives, this is a function, and it's an entry matrix, which is a function of Q, Q dot, and Q double dot. Now, what is the information that I need in order to compute the jerk of the end effector of a robot? I need to know what is its configuration at one instant. At the same instant, I need to know what is its instantaneous velocity in the joint space. Not only, I need also to know what is its acceleration in the joint space. Then I command the jerk in the joint space, and only then I can compute this. Of course, if I'm starting from rest in the sense that velocity is 0, acceleration is 0, and that's it, in the joint space. So all these terms are gone. I apply now a jerk in the joint space, and I need to know only the configuration from where I start to compute the jerk at the Cartesian level. So you see that things get involved, but this is the nature of the differential kinematics. Another, okay, and you can continue. Unfortunately, there are no, as far as I know, no Italian words for these two terms. So we stop at velocità, accelerazione. There's no term for jerk or for snap. Contraccolpo. Contraccolpo seems something which is against, but may help instead. So, well, probably. Okay, but last things to comment is very important from a, let's say, computational point of view and also from a physical point of view. Namely, look at this. No matter which is the order of differentiation that you want to link between joint space and task space, you always have the Jacobian as the leading term. Okay? So these are additional terms, but the Jacobian is always there, the Jacobian that you compute at the velocity level. This is why it's so important. And in fact, all information is already there inside the Jacobian because all the other terms comes from differentiation of this. Okay? Not only, if this Jacobian is singular, then you can move to higher order, but you will always have singularity between the same differential order. Okay, so if the mapping at the velocity level is critical, there are some singularity for any reason in the configuration of the arm, you will have to live with this even if you move to higher order. Still, you cannot, for instance, you cannot invert this mapping if this is a square matrix because the Jacobian may be singular when it's singular, but you cannot invert either this mapping. Okay, and order this, and so the first order approximation, and now you can think about system theory, is very important because this first order approximation occurs at any level. So if the linear approximation of a system behaves badly, then you cannot say something in general. You have to go case by case to study, for instance, stability or instability and so on. If the first order approximation, which is in this case represented by the Jacobian at the velocity level, is well conditioned, then you have no problem. Of course, there are other contributions to be included, but regularity is guaranteed, for instance, when you're trying to invert these mappings. Okay. So, I would like to conclude with a small primer on linear algebra. It's something that you should know. Why I'm doing this? Because now the properties of this Jacobian matrix, which changes with configuration, but it's when you take a picture at one configuration, it's a matrix of number. When you evaluate J of Q in a given Q is a matrix of number. So as a matrix of number, it has some geometric spaces associated to this. What is you should know from basic concept of algebra. So I'm taking a generic matrix which I call J because in fact I have in mind the Jacobian, which has m rows and n columns. And now what can I define? I can define the rank of this matrix, and here are some definition and some way to some comments that you can make it. You can define the range of this matrix, which is a subspace. Here I'm writing it explicitly. So it's all vectors in the destination space. Think about joint space and Cartesian space. So all vectors in the Cartesian space that can be generated with some vectors in the starting space, which is the joint space. Okay? So it's very important to understand if I can generate some Cartesian velocity when I'm in a given configuration by some joint velocity. And this space is the range space of the Jacobian. And similarly, I can look at the kernel or the null space of this matrix, which is all, in our interpretation, is all joint velocities that when you execute this, they will produce no velocity at the level of the end effector. Seems strange, but it's possible. Okay? And then you have other properties between these subspaces. Pay attention, these are subspaces, so they, if you combine two vectors in the null space, you obtain a new vector in the null space. So if you have some joint motion, for instance, my arm, which is highly redundant, if I'm looking at the end effector velocity and I'm doing this motion, okay, I'm moving my joints, but I'm not moving the end effector, which means that my vector of joint velocity is in the null space of the Jacobian of this mapping. Okay? So if I have some instantaneous velocity which does not move this, and some other velocity that does not move this, if I combine this, I will generate a new velocity vector in the joint space that will not move the end effector. This means being a vector subspace. Okay? So you have these properties. We can compute this using Matlab. And before doing this, I will conclude today, because by some numerical experiment, or computation experiment is too much, but pay attention what are these subspaces. This is a nice pictorial view. So if our matrix of interest is the Jacobian that we have already considered, so it takes inputs from the joint velocity space. So for a given configuration, this is a matrix of numbers. So it takes all this green joint velocity out of a bag, so any combination that you can imagine, and it maps it into Cartesian or task velocity. But in general, it may not cover all possible Cartesian velocity. It just covers those which are in the range of the matrix. The other are not realizable. No matter how I choose my joint velocity, I cannot generate that Cartesian velocity. I can only generate Cartesian velocity which are in the range of the Jacobian. Of course, if the range of the Jacobian is the maximum possible, I cover all possible velocity. Otherwise, I have a loss of mobility at the end effector level. Okay? This is why it's so important, the range. Not only, but if the Jacobian typically has more columns than rows, so it's a matrix like this, with m, n, and m, or strictly less than n, then I will surely find some joint velocities which do not generate any Cartesian velocity, which means that they map the green area into the zero, which belongs to the subspace, like all linear spaces have the origin inside of this space. So they don't move the end effector. So there will be some non-zero joint velocity that produce zero Cartesian velocity. Of course, including the zero joint velocity. If I don't move the joints, nothing happens. This is clear. Zero maps into zero. But there may be other joint velocity that do not move the Cartesian task. Okay? And these are the null space, and these are also important. Okay? So null space and range space of J are very important. Pay attention, this is not the only situation where you can have a non-vanishing null space. The same happens if you have a square Jacobian. So let's say a 6 by 6 Jacobian, and the determinant of the Jacobian is 0. So you have a singular situation. And now the singularity becomes an important object. All what we have said until now converge to something which is mathematically important. So we have a matrix, and we can define if this matrix is singular or not by looking at the determinant. And if this is the case, it means that in that configuration, the robot loses some possibility of moving its end effector in some direction. So this is fundamental, because not being capable of moving the end effector, although I can move the joints at any place, but the end effector can move only in some subset of direction, means that I cannot, for instance, take an object which is close to the end effector in that direction. I should change configurations and do something else. So it's very important for programming, for controlling motion, for anything that I can do. Okay? In fact, crossing this singularity is critical. We will define singularity not only in the case of a square matrix, but also when this matrix is not full rank. And if the matrix has less rows than columns, because of the definition of the rank of a matrix, at most it can have a rank equal to the number of its rows. When the rank is lower, it means that in the m-dimensional space of destination, so the task space of interest, we cannot access any direction. So when the rank is not full, and this definition applies to a square matrix or to a non-square matrix, then you lose mobility of the end effector. In the joint space, you can continue to do whatever you wish, but you cannot generate something that you desired arbitrarily at the end effector level. And in fact, this problem becomes essential when you're specifying the task in the Cartesian space. You say, okay, you're there. Now you have to move in this direction. Oh, this is not in the direction of the range in this configuration, so I cannot achieve this. No matter how fast or how combined my joint motion, I will never achieve this. Now, the nice things that will be used later is some property of duality. Pay attention. This back map is not with the inverse or a pseudo-inverse of the Jacobian. It's just with the transpose of it. And we will soon learn that this is, in fact, a mapping between so-called force spaces. I think it's, here it is. Okay. So since those conditions should be known to you from linear algebra, if you take a matrix and you sum the null space of the matrix and the range of its transpose, then you obtain the whole starting space Rn. This is a direct sum. So assuming that this has dimension n and this has dimension m, then this holds, and a complementary relation holds also in the destination space. If you take the null space of the Jacobian transpose, remember that the Jacobian transpose is a matrix like this, so it takes m vector and maps it into n vector. So here I'm in an m-dimensional space. If I take the null space of the Jacobian transpose, which is something that lives inside Rm, and I make a direct sum with the range of J, which is the destination here, so it's again in Rm, I get the whole space. So these two relationships are known from linear algebra, and in robotics can be interpreted the J mapping in terms of velocity and the J transpose mapping in terms of forces. So if I'm considering the null space of J transpose, so something in the Cartesian space, this will be a subset of forces, Cartesian forces, that are mapped into zero joint torques. And we will see what this means. And similarly, if I look at the range of J transpose, so I consider all possible forces applied to the end effector, I will get to some range of J transpose in the joint space, which are the set of all needed torques that balance those forces. This problem is relevant in statics that we will see pretty soon. Okay? So I would, these spaces, pay attention, are dual spaces. In fact, I'm interpreting vectors here as joint velocities, as Cartesian velocities, while I'm interpreting vectors here as forces. So in fact, forces are not velocity, although they are vector living in the same dimension. M here and N there. Joint velocity are not joint torques, although they are n-dimensional vector. Why is this? Because these are linear spaces, so I'm confusing the space with its tangent space. In fact, the duality holds at the tangent level, if this reminds you something from linear algebra. Otherwise, just forget what I've said. So I think that at this, okay, I can just show this result. This is exactly the summary of what I've told you in words. So I can define the range of the Jacobian. I can define the rank of the Jacobian. I can define the null space of the Jacobian, the null space of the Jacobian transpose, and so on and so on. And of course, they are locally defined. They depend on the configuration, because the Jacobian is a function of the configuration. And the Jacobian transpose, which is just exchanging rows and columns, is the same. So the range of J is the set of all generalized velocity, because I don't know if they are linear, angular, whatever they are, that can be instantaneously realized by choosing an appropriate value of the joint velocities. If we have a loss of rank, we are in a singular situation, and that it means that there exists some direction where we cannot move instantaneously. Okay? And we will see later on what does it mean, while when the null space of the Jacobian is different from the zero vector, because the zero vector is always in the null space. I don't move the joints, I will not move the end effector. But then there could be some motion of the joints, and these are called self-motion, in fact, that will not produce a velocity at the end effector level. Okay? I think that I can now show you some results. Okay, here I have a small piece of Matlab code where I consider a planar 3R robot. So with unitary links, I guess, yes. So I'm in this situation. I have some base, then I have a link, a link, a link. So this is Q1, this is Q2, this is Q3, and these are theta angles of the Denavit-Artenberg convention. And then I consider, so Q is Q1, Q2, and Q3, and Q dot belongs to R3. And now here I'm considering only P, which is Px, Py, and this is in R2, is in the plane. So when I'm computing the analytic Jacobian, which maps joint velocities in R3 to end effector linear velocity in R2, this Jacobian is this form, and it's a 2 by 3. Okay? So I'm doing this, and then I select a configuration, and we will see now a first case when I take this configuration, 0 pi over 2 pi over 4, which means that this robot, if this is the x0, y0, so this robot in the first case is in straight, then what is pi over 2, and then pi over 4 is in this configuration. Okay? And we will see in this configuration what happened to the Jacobian. If it's full rank, what is its null space, what is its range space, what is the Jacobian transpose null space, the Jacobian transpose range space, the dimension, and if the sum gives in the proper space 3 if we are working in the joint space, or 2 if we are working in the task space. Okay? And then we will change situation to a new configuration. But let's start like follows. So I'm running this simple program. So here you see, this is the direct kinematics computed symbolically. Then I take the symbolic derivative with respect to Q, and this is an instruction that you can have. And this is the Jacobian. Okay? Jacobian has 2 rows and 3 columns. This is the first column with a comma. This is the second column, and this is the third column. So you see, for instance, this is what we compactly write C123, because it's cosine of Q1 plus Q2 and Q3. Now I evaluate this in this configuration. Let's write the configuration. This is Q0 pi over 2 pi over 4. And if I evaluate this in this configuration, I obtain, I don't know if you see it from the distance, but it's minus 1.7 whatever, minus 1.7, 0.7, and then 0.29, and so on and so on. Okay, this is typical square root of 2 over 2. Okay. So this is the Jacobian. Now, my question is, if I'm applying any joint velocity here, moving these 3 joints, can I go everywhere with the end effector? The answer is yes or no, depending on what? Depending on the rank of this matrix. Because if this is full rank, then I can access the 2-dimensional space of Cartesian velocity, so I can go everywhere. Okay? So these are the questions. And then the other question, for this robot, can I move its joints so that the end effector does not move? Which means the null space of the Jacobian is different from just the 0 vector. And the answer is again yes. In fact, you can see it here. No? You can play around like a parallelogram and move this joint so that this end effector remains there. Okay? And this is because this is a 2×3 matrix. So it's always possible. So let's see that if this intuition is correct. So first we compute the rank, and the rank is 2. Cannot be larger than 2, because this is a 2×3 matrix. So we are in the non-singular case. And the null space, this is another operation that Matlab computes easily. The null space, it gives you a base for the null space. So a vector, a unitary vector, actually, if you take the norm of this vector, is unitary. But it gives one direction, which means that if you move the joint 1 at the speed which is 0.3 whatever, the second minus 0.6, and the third plus 0.7, then the end effector velocity will be exactly 0. But this is not just one velocity, because if you multiply this by a factor alpha, it's exactly the same. Okay? So there is a one-dimensional subspace of joint velocities that do not produce instantaneous Cartesian velocities. Okay? And this is so because this is full rank and this has 3 columns, and in fact the difference between the number of columns and the rank is exactly the dimension of this null space. Okay? In fact, dimension of null space 1. So check, I make a check. So I take this velocity and I multiply by j. So this is a joint velocity in the null space. This is what the Matlab program is telling me, so I don't believe it. So I multiply by j, and I should have 0. Okay? So I do this computation, and I don't get 0, but I get 0.1 to the 10 to the minus 15. Why is that? Because, of course, I'm doing numerical approximation, but this is practically 0. Okay? Now, range. This is more critical. Pay attention here, because this. So I can compute the range of this 2 by 3 matrix, the one that we showed before. And here, as before, Matlab provides me a basis for this subspace. So it provides 2 independent vectors of unitary length with which you can describe whatever vector in this 2-dimensional space. So these are not really relevant per se as vectors. It just says that there are 2 independent vectors. They may not be orthogonal. In fact, they are not orthogonal, I guess. Okay, but they are independent, so this means that the range space has dimension 2. In fact, the rank of this matrix is 2, so I can generate any velocity at this level. So the dimension of the range space is equal to 2. Now let's look at the Jacobian transpose. If I take the Jacobian transpose, I just reverse columns and rows. The rank does not change, of course, because it's the maximum number of independent rows or columns, so this transposition does not change things. But the subspaces changes, because the null space of J is not the null space of J transpose. Starting from the fact that they live in 2 different dimensional space. The null space of J is in the joint space of dimension 3. The null space of J transpose is in the Cartesian space of dimension 2. So they are 2 different objects. Okay? So let's see. This is the Jacobian transpose. JT is just the previous matrix where I exchange columns and rows. So it's a 3 by 2 matrix. And I do exactly the same, range of J transpose, rank of J transpose, but I knew already that it was 2. Null space of J transpose, pay attention. The answer is empty matrix. Why? Because this is full rank. So if I take a 2-dimensional vector here, which I can interpret physically as a force, I cannot generate, if this vector is non-zero, I cannot generate a 0 vector, because these are full rank. So there is no possible combination of the 2 columns that's zeros. These are independent columns, which means, we will come back on this later, which means that if I push with a force, no matter in which direction I push here with a force, there will be always the need of some torque here to balance this force, otherwise the robot will move. Okay? And this is exactly because we have a full rank Jacobian. When we do the transpose, we have this situation. So this is not unexpected, but should be interpreted properly. So the dimension of the null space is 0. There is no basis vector that can describe this. The range of J transpose, okay, here I have 2 vectors which are the basis for this. I don't care about which vector. This is computed numerically, so they are normalized, they are not orthogonal, but there are 2 independent vectors. So I can say that in the destination space of the mapping Jacobian transpose, which is a 3-dimensional space, there are 2 independent vectors at most. So the dimension of the range of J transpose is equal to 2, and not 3. And it cannot be larger than 2, because I have only 2 vectors in the J, 2 column vectors in the J transpose. So more than combining this, I cannot generate more than 2 independent vectors. Okay? So this is done. Now we do the final check. We test if these dimensions are okay. So we're starting checking in the joint space, which is of dimension 3, and we look at the dimension of, this is in this destination space of dimension 2. So the sum of the dimension of the range of J, so all the possible velocities that I can, the space of all velocities that I can reach, plus the dimension of the null space of the J transpose should give 2. This is the theory, and this is the answer is correct. And similarly, if I check the sum of the dimension of the null space of J in the joint space of dimension 3 and of the range of J transpose, again in the same dimension, this should cover all the dimension of the joint space, so should be equal to 3, and in fact, this is correct. This is always the case, okay? Now, consider a second case, and we do exactly the same thing, only changing the configuration. And this configuration now, it's, I'm changing this, and then I'm launching again. So this is the same robot, same Jacobian. Now we're changing the configuration. The configuration now is the following. It's Q equal pi over 2, 0, pi. Pi over 2, 0, pi, which means that I'm starting from here. So I'm rotating by 90 degrees the first link. Then I have the second link straight. And then I flip over the third link and I come back like this. So the robot is straightened in a vertical configuration. So it goes up with the first two links, and then the third link is completely folded. Okay? So if I evaluate the Jacobian, this is very simple now. Look at this. It's minus 1, 0, 1, and the second row is completely 0. So let's write it explicitly, because then we can make computation. So the Jacobian in this case is minus 1, 0, 1, and then 0, 0, 0. Now, we don't need Matlab to do this, but we will do it anyway. What is the rank of this matrix? 1, because there's only one. Okay. So dimension of the range space will be 1. There's only one that, in fact, no matter how I instantaneously give velocities to this, since there are 3 zeros here, I will never generate a velocity in this direction, in the y direction. Okay? It's like a locking position. Instead, I can generate velocity in this direction for the end effector in multiple ways. Not only, if I'm moving joint 2, since there are 2 zeros here, this will not affect instantaneously, pay attention, neither this direction nor this. So I don't move the Cartesian end effector by moving joint 2. Joint 2 is completely useless. Of course, as soon as I give a velocity to joint 2, I will change configuration. So the Jacobian will no longer be this one. And so I have to do a new evaluation. So this is really an instantaneous situation that I can depict. One may say, well, but I'm very unlucky to be in this situation. Okay, so it's only very local. What happens? Well, as a matter of fact, even if I'm not exactly in this situation, but pretty close to this, I will have problem in inverting the kinematic mapping. So velocities that are close to be irrealizable at the Cartesian level will need a huge amount of joint velocity to be realized. So in practice, it's like being in a singularity. So it's not just the point, it's around the singularity that problem arises, and this is why we need to study these cases. So with this in mind, I compute the rank, and the rank is 1, as expected. And I can compute the null space. Now pay attention. Remember that in the full rank case, the null space had dimension 1. Now in the singular case, the null space has increased dimension. And if I look at two possible bases, the number is not important, but I can recognize that one basis vector for the null space has the same number here, which means that if I'm moving the three joints at the same velocity, at exactly the same velocity, this will give no velocity at the end effector. And then there's another combination, plus minus plus by suitable product, that again will give no velocity at the Cartesian level. And even if I combine these two directions, I will generate another joint velocity that is not giving velocity at the end effector level. Now the dimension is 2. So it's increased because of the fact that the rank of the matrix is lower than the full rank. So dimension of null space is 2. Again, I don't believe that. So I take, in particular, these two vectors, which are a basis for the null space vector. I multiply by j, and I obtain something which apparently is non-zero, but is multiplied by 10 to the minus 15. So again, up to rounding of numerical errors, this is correct. Now, range of j. So how many independent columns can you find here? This is gone, and these two columns are equals, opposites. So in fact, I can take this or this to represent all possible direction. In fact, there I have minus 1, 0. I could have had 1, 0. It's not important. It's just one direction. And the one direction of the range is this one. And in fact, I can see here, I have a non-zero component along the x-axis and 0 along the y-axis, which means that the only velocities that I can generate at the end effector level are plus or minus in this direction. Okay? Dimension 1 instead of 2. So I'm losing mobility at the end effector level. Same thing about the Jacobian transpose. So I transpose the Jacobian, and now I have, instead of having a row of 0, I have the second column, which is 0. And of course, I will have a non-zero null space, because if I take something which has 0, 1, so the 1 will hit the 0 column and will generate 0 joint torque, which means that if I'm pushing with a force in this direction or in this direction on the end effector, because of this locking condition, these forces will generate no motion, so they don't need to be balanced by joint torques. You see the point? If I'm pushing here, the robot will move unless I apply a torque which keeps it in balance. If I'm pushing here, the robot will not move, and I don't need to add joint torque for balancing, because these forces will be balanced by internal reaction, so by the fact that the robot is a rigid body. Okay, so this follows from this simple analysis. So the rank of J transpose is like the rank of J is equal to 1 in this case. There is a null space of J transpose, a one-dimensional, 0, 1, exactly like I expected. It's a unit vector in this direction. It's dimension 1. The range of J, of course, I don't care about, of J transpose, I don't care about this column, it's just this direction. And pay attention, I could have taken the first column of J transpose, minus 1, 0, 1, which is exactly what I find here, only this is scaled because this is normalized to have unit norm. This is a computation inside Matlab. It only provides basis vector of some subspaces which have unitary norm, just for normalizing things. So it's only one vector, so the dimension is 1. And the final check, as before, if we sum the dimension of the range of J and of the null space of J transpose, I should find 2, because it's in the Cartesian space. And in fact, this is 1, and this is 1, and so I have 2. And if I do the same in the joint space, so the dimension of range J transpose is equal to 1, and the dimension of the null space is equal to 2, if I sum it, I get 3, which is equal to the dimension of the joint space, as expected. So no matter if you have a regular situation or a singular situation, those identities always hold. But it's the subspaces that change direction and significance. So this is a complete analysis of a simple case, but should be always kept in mind, even when we are dealing with, more and more when we're dealing with robots with multiple degrees of freedom, like the KUKAs that we have in the lab. Okay. I think that we can stop here. So have a good weekend, and we'll meet on Monday.